terms. So today we're going to talk about pointers and references. So a lot of people today spend their lives in languages like Java, C#, and JavaScript, and so on, where pointers and references are largely hidden from you. So even if you kind of worked with C or C++ in college, maybe you've forgotten some of this stuff. So it can be important and useful to review, because pointers are always there and somebody has to deal with them, as James Mickens has said. So these two terms are sometimes used interchangeably when people aren't being careful and pedantic. But there's a difference, and we'll talk about that today. So let's start with pointers. So a lot of languages don't expose pointers to you at all, especially garbage collected languages, and we'll talk about why. But here in C or C++, you can use pointers, look at pointers, do whatever you want to pointers. So we have a simple program here. We have the value x, and we have a pointer to x. And we're going to print out x, and then we're going to print out the pointer to x. And this syntax, so int star means we have a pointer to an int, and the ampersand, the way you can remember it is ampersand starts with a, so it is address. So ampersand of x gives you the address in memory of this variable x, stores out an x pointer. And with printf, you can use %p to print out a pointer type. So let's give it a try. All right, so we get x is equal to 5, and we get this value for the address in memory of our pointer. So this is like actually in RAM, where is 5 being stored. Okay, cool. So what can we do with pointers? So in C, you can do whatever you want. C and C++, you can do whatever you want. So for instance, we could say x pointer plus plus to add 1 to pointer. And that's totally fine. All right, so this value would be have 1 added to it. We can also dereference pointers. So if we want the value back from a pointer, or we want an integer back, we can dereference the pointer. That means getting the value that the pointer points to, and you do that with the star operator. So it's a little confusing because a star tells you it is a pointer, and then a star makes it not a pointer anymore as well. All right, so when you do this operation, because we are an int pointer, when you do this, it tries to take the value in this memory and make it an integer now. So let's see what we get. We get 5 back, right? That's what we expect. But a pointer doesn't really guarantee that this is actually an integer, right? We could say that this is a float, right? And C will complain here, right? But we could cast this to a float star just to force the issue. Now when we dereference it, it's going to be treating the data stored at that memory address as a float, and you get back something that's garbage. Or actually, probably try to do that. %f tells printf it's a float. Right, so it's no good. It's one of the ways pointers can be dangerous. Another thing you can do, we showed before, is you can change the pointer, right? You can do pointer arithmetic. Now what's going to happen when we dereference our pointer? Right, who knows? Like that, that pointer now points to a new memory address, not one that we actually allocated necessarily. And it's just taking whatever bits happen to be in that memory and trying to represent them as an integer. So we get garbage. This could also cause a crash if you went into memory you don't actually have access to from your program. But we got lucky and we just got a bad value, right? So that's why pointers are kind of dangerous, but they're also useful. So why are they useful? So let's say we have a large, let's say we have a function called add1. Takes in an integer, right? We do x plus plus to add 1 to x. And we've got our x equals 5 here, and we call add1 on x. And most people will be familiar with the fact that when we pass this x, we're passing by value. We make a copy of this x into this function. And so this x plus plus is only adding 1 to the copy, right? So when we print x here, we're still going to get 5 because we didn't pass a pointer to x, we just passed x. We just get 5. So one way a pointer can be useful is we can change the semantics of our code, right? By passing add1, we can now add 1 to x. Now I need to be careful, right? This actually won't work. This will be incrementing the pointer, not the value. All right, so that's not going to do anything. We're still going to get 5. We want to dereference x and then add 1 to it. And now, let's do it like this. And now we get 6. Okay, so that's one way a pointer is useful, is you can have semantics where you can pass a value that gets changed by a function. And the other way it's useful is if you have a big struct, right? Maybe it's a 4-dimensional, maybe these are doubles, maybe even bigger. Right, double x, double y, double z, right? That's a big chunk of data, and if you pass data like this by value, it's a lot of data to copy, right? You've got 64 bits for each value, a lot of data to copy. And if you pass a pointer to this, you're only passing a single 64-bit value or 32-bit value if you're doing a 32-bit program. So yeah, pointers are useful because you can do semantics that actually change the value, and they're useful because you can pass a single pointer around instead of a whole bunch of data. The other way they're useful is for recursive data structures. So if you were to define a binary tree entirely by value, right, without pointers, you're going to have some problems here, right? So a structure like this, a node contains a left and a right node, and the left and right node contains a left and a right node. So this would be a data structure that contains takes up like infinite space, right? So a language has no way to represent something like this. So instead, you could take pointers to those things. So a node just contains 2 pointers. That's no problem. So that is the motivation. And if you've been programming in something like C# or Java, what is going on behind the scenes? So in C# every single class, and in Java every single class, when you work with it, you're sort of working with a pointer, but it's not quite a pointer, it's really a reference. So what's the distinction between pointer and reference? So the pointer, you noticed, we could do whatever we wanted to it, right? We could say, right, we could do arithmetic on it and change it. So a pointer just points to a location in memory, period. A reference points to an object, right? It points to a thing. So if we made a reference instead, And in C++, you can do a reference like so. And we can print out that reference. Okay, so we get 5 from our reference to x. Behind the scenes, is sort of the same thing is happening, right? Xref is storing the memory location of x, but it's not going to let us do things like this, right? If we increment xref, we're actually incrementing the value, right? We're not changing the memory location. We can't get garbage from it. And so a reference is like a safer pointer, right? It points logically to the x rather than actually to a point in memory. And in C++, that's mostly used to have a little bit of extra safety. It can help you prevent having null pointers, because a reference won't let you directly point to a null location in memory. But in languages like C# and Java, it's actually pretty important. And the reason why is because things can get moved around in memory by the garbage collector. So we have a player here. We made a new player. And our P is basically a reference. So it acts like a pointer in a lot of ways. And we can actually get the pointer value in C# with some tricky stuff. Right? We can get a handle to it and get a int pointer from that handle and print it out. So let me run this real quick. All right, so we're actually seeing the memory address that our player data is located at. But what you have to keep in mind is at any moment, the garbage collector could run and that memory address could change. So you wouldn't want to actually do anything with this pointer unless you first told the garbage collector not to move it around, which you can do that in C# with unsafe code. And you need to talk, if you want to like pass data from C# to C, you need to tell C# not to move it around, because C will have no way to know that your data can move. So player is really a reference. So that means you get the same benefits as a pointer. That means you can pass P to a function and change P, and your P will change. And when you pass P around, you're only passing the 64 bits or 32 bits of memory location to the function. But it is pointing to the player, not just to raw memory. So when the garbage collector moves it, P will still refer to the right thing. So basically, if you're using Java or C#, everything is a reference all the time. Of course, in C# we also have structs, which are value types. In Java, you don't have that. So the pointers are there, but they're kind of hidden from you behind a reference. And that means in C, right, we're in C we had to worry about if we made a binary tree. Right, we had to worry about whether we had nodes or pointer to nodes inside. So the benefit of sort of having everything as a reference is everything makes sense all the time. All right, that'll just work because everything's always a reference. But in C#, right, we could do struct node. Right, now it's a value type, and now the compiler is complaining. Right, we have a cycle in our struct layout, so we can't do that. Any questions about pointers and references? If anyone has questions, feel free to type them up in chat. A little more detail here. In languages like C# and Java, when you have one of these reference types, like a class, they go in the heap in memory. That means they can be allocated anywhere in RAM. So if you have something like an array of players, That means you have a contiguous array of references to player objects. Right, so you've got something like a reference to a player, reference to player 2 in memory. But those references could point all over memory, right? It could be anywhere in the heap, all over the place. If player were a struct instead, if we make this a struct, then you would have actual player values in memory, all contiguously. And when a CPU requests data from RAM, it takes a long time. And when it does it, it goes ahead and gets a big chunk and pulls a big chunk of that RAM ahead of what you asked for into the CPU cache. And so if your data is small enough, and if you're tending to access them in order, using a value type over a reference type can be much faster, because everything here is in order in memory, right? Your frags on your name are all in order. Whereas if it's a class, right, and you have these references, and each player could be in a vastly different area of RAM, and so they're not always in the cache. So sometimes you have to wait to get your next player because it's not in the cache. You have to wait a long time. So that's something to think about, right? When you have pointers to things, you're usually pointing to things in the heap, and that can be slow. All right, I'll wait around a minute for questions, but if there's not any, that'll be it. All right, that's it for now.